This is the next video in the chapter on electronic structure and periodic properties. In the last video, we were talking about modeling an electron as a standing wave and using a wave function to describe where it's located. And now we're going to condense where it's located into 4 quantum numbers. So in the last video, we stated that an electron lives in an orbital, according to our most up-to-date model of the atom. So it lives in an orbital, and an orbital is described by a wave function. A specific mathematical equation that describes that orbital shape and energy. The problem is there are a lot of different orbitals, and that means there's a lot of different wave functions, and we need to know specifically in which orbital does a particular electron live in. And so in order to specify, we need to specify the wave function, but the wave functions are so scary and long and complicated that I didn't even include them in the last lecture video. So we certainly aren't going to include them every time we want to talk about an orbital. Instead, we're going to specify which orbital we're talking about with the 4 quantum numbers. So in a way, 4 quantum numbers are like an electron's address. Much like the street address you would use to receive mail or to tell someone where you go to school. Quantum numbers specify where an electron is located. We're going to take the analogy all the way. Here's an address, a street address that you should be familiar with. The address for the Lawrence Campus Center. 711 East Bolt Way, Appleton, Wisconsin. So if somebody asked you where you went to school, you would give them some portion of this information, depending on how familiar they were with Bolt Way, Appleton, Wisconsin, or the United States as a whole. And so each of the quantum numbers is kind of like a piece of a street address, with each of the numbers progressively giving more and more information about specifically where an electron is located. So we have N, L, M sub L, and M sub S, going from least specific to most specific. We're going to work through one quantum number at a time and talk about what it is, what its value is, and what it means. And then we'll summarize that information as we go in this table. So the first quantum number is N, and it is called the principal quantum number because it's the first, most important, and the oldest. The value for N is any positive integer, starting with 1. And we use this quantum number to tell us about an electron shell, which gives us information about the size and the energy of the orbital. All right, so information about the principal quantum number tells us about the shell. So the values for this number start at n equals 1, and they increase to 2 and to 3 and so on to bigger and bigger atoms. And the concept is one we actually talked about a little bit earlier when we talked about the Bohr model of the atom. So we're going to draw that again here to spark our memory. So remember when we drew the Bohr model of the atom in our captain's log of what does the atom look like? When Bohr hypothesized that each electron followed a circular orbit around the nucleus, like a planet orbiting a sun, with the nucleus in the center. Nucleus here, positively charged. Electron on one of these orbits, negatively charged. So Bohr described these different orbits as quantized energies that an electron could have, and that part is still correct. And he labeled each of these possible energies and each of the possible orbits with a principal quantum number. So the orbits or the orbitals that are closest to the nucleus have the smaller quantum numbers, and the farther from the nucleus have the larger quantum numbers. So we'll write that here. The farther from the nucleus, the larger the size, the larger the radius. And because the larger the radius, the electron spends most of its time far away from the nucleus. And when the negatively charged electrons are far away from the positively charged nucleus, they're destabilized. They prefer to be close together. And so that electron orbit that's far away from the nucleus has higher energy. If we want to look at one of the closer orbits or orbitals, these are smaller in size. They have a smaller radius, they're more tight and close to the nucleus, and that's more comfortable. So that's a lower energy orbital. So the closer you are to the nucleus, the more stable that position for an electron and the lower the energy. And that's the concept that this N represents. It tells us about the size of the area where we could find it and the energy level that it will have when it lives there. Another important information that we get from the N, the principal quantum number, is about the nodes. So remember a node from when we talked about standing waves. A node is a place or a space with 0% chance of finding an electron. So when we drew the microwave, we said if there was a node, that this was a place where the food was going to be cold because the amplitude was 0. This is kind of the same thing. It's just in 3 dimensions. It's a 3-dimensional space. We're just going to change that. 3-dimensional space where there's a 0% chance of finding an electron. So the number of nodes for an atom, or for a particular orbital, sorry, is n-1. And while we're talking about this circular, spherical looking atom, we can go ahead and mention radial nodes. So there are 2 types of nodes: radial nodes and angular nodes. So a radial node is spherical, as the word radial indicates, and you can calculate that as n minus L minus 1. So let's take a look at a radial node. Here's a picture of a couple of different orbitals, and some of them have nodes in them. So we can tell as the size increases, we have the same shape, different size. That means that the principal quantum number is changing. So this smallest one could be n minus 1. This next larger one could be n minus 2. And this bigger one could be n minus 3. But notice that you can see each of the orbitals that came before inside of these with a node in between. So this guy right here, the n equals 1, is going to have 0 radial nodes. The radial nodes are come after each of the different subshells. So the n equals 1 subshell is here, and there is no radial node before that one. For the next one, n equals 2, this is the n equals 2 part of the orbital. This is the n equals 1 part of the orbital in the center, and in between the n equals 1 and n equals 2 orbitals, the shells, there is a radial node. So there's 1 radial node in this one. And then over here in this biggest picture, this is an orbital that has a 3rd subshell occupied. That's the biggest region. So this is the n=3 shell. Inside of that is the n=2 shell. Inside of that is the n=1 subshell. And between shell 1 and shell 2 is a radial node. And between shell 2 and shell 3, there's a radial node. There are 2 radial nodes here in this picture. And it does look like a circle because I am drawing it on a 2-dimensional piece of paper, but in real life, a radial node would be 3-dimensional. It would be a spherical. You can picture it as an orange with an orange peel on the outside, and that orange peel surface, that would be a radial node. All right, back to our list. So the quantum number tells us about the number of nodes in total, and we just looked at what a radial node looked like. And so now let's summarize what electrons with the same principal quantum number have in common. Electrons with the same values for n are going to have similar energy. Not exactly the same, but close, relatively the same. So, same n value, similar energy. And the analogy here, if someone asked you where to go to school and they weren't from the United States, you might tell them you go to school in Wisconsin. So these electrons would be in the same state. Because that's probably enough information for someone who isn't very familiar with Wisconsin to get an idea of where you live. In the next video, we will talk about the next quantum number, the angular quantum number L.